Okay, today we are going to be diving into something called dynamic linear models. And by the end of today, you will see the connection between dynamic linear models and the kind of normal state space models that we've been doing. But initially, they will look very different, I suspect. Because the format and the thinking about the way we deal with things like covariates and parameters and whatnot is very much different from the typical state space models. So today, we're going to talk about DLMs in great detail. First, we'll think about them in a univariate response framework. So the dimension of the y is just going to be 1. We're going to only think of one observation at any given time. And then by the end of the lecture, we'll sort of expand that to a situation where you might have multiple observations at any one point in time. So we're going to talk about stochastic level and growth models. Then we'll talk a little bit about dynamic regression and how to use seasonal factors in those dynamic regression models. Then we'll get into a little bit of forecasting with dynamic linear models and just talk briefly about model diagnostics. Before I go real farther, I'm just going to remind everyone that if you had something like a times x and you wanted to know the variance of a times x, this equals right. So just keep that in the back of your mind, because when we get to the forecasting stuff in particular, we'll be using that idea, but in matrix form. So just keep that in the back of your head. Okay, let's begin with everyone's favorite models, linear regression. Everyone's seen these in probably great detail, way more than perhaps you ever wanted to. The idea in a linear regression model like this, where we've got some observation with an index I, and we have an intercept and a slope, and then some predictor variables. The data, the predictors, and the errors all have some index I that really in this context doesn't mean anything. It's just literally an index. So if you had a data frame with a column of Y and a column of X, if you shifted the order of those rows around, it wouldn't make any difference to the inference, right? Models don't care about that. So that is a little bit different when we deal with time varying models. So to motivate that, we're going to look at this. So let's write our linear regression model in matrix form. And in order to do that, we're going to imagine there's a 1 here behind this alpha, and we're going to group the 1 and the x. So we'll pull that out right here. So here's for our intercept term. There's our predictor variable, and then we've got our intercept and our slope. Right, so we would take 1 times a plus x times b, and that's this model right here. If you wanted to write this more compactly, we typically think of vectors as being column vectors. So we're going to just transpose this. We'll call this x, but put a transpose on there. So we're thinking about a row vector now. And we're going to call this vector of our parameters theta. So that's all the definition is right down here. So x transpose is just a row vector now with the intercept term, a 1 and a covariate x. And theta is now our parameter vector. And I should back up for just one second. The reason I'm doing this is because the literature on dynamic linear models tends to use this notation. It's a little bit unusual for us to be writing things out with a lot of transposes in main terms, but we're going to follow the convention here. Okay, so in a dynamic regression model, the idea here is that we'll move from a situation like this, where we've got an observation, some numbers of predictors, some parameters, to a situation where we've got data, predictors, parameters, but now our parameters are going to be dynamic. They're actually going to be a function of time as well. And here I'm writing this model with T subscripts now, because we're thinking about dynamic meaning changing over time. 2 important points to note here. In this regression model, the T subscript here tells us something about time. And that should tell us that there's actually some implicit information in the time ordering of the data. So in this type of model, actually shuffling the order of the y's and the x's would have an effect on what we're trying to do, because the parameters themselves are not static. Those are also changing. Okay, the second point is that the relationship between the observation and the predictors, or this could even just be an intercept, is going to be unique for every time step. Okay, so we're going to subscript the parameters here with a t. That means just as the data or the predictors change at every time step, the parameters change at every time step. Okay, if you think about this model though for a moment, we've got a apparent problem when it comes to parameter estimation. So we'd like to know what these things are based on a vector of y and essentially a matrix of x. And I'm wondering if there's anybody who has an idea just offhand what that might be, just thinking about this model. We've got data at time t, predictors at time t, and parameters at time t. And we don't know what any of these are. We know what the y and the x are, but we're trying to estimate these.
Is it because there's an infinite number of combinations that can give you every y?
Well, not close, Marcus. You're onto something there. But the idea is that in reality, if you think about this, we only have one data point per time step. So you'd only be able to estimate one parameter from this model, right? And you'd have no uncertainty in that because we burn all our degrees of freedom up. So while this model looks great, we're going to have to do something about that in order to be able to estimate these parameters. So what we do is we're going to constrain the parameters of this model to be dependent on one another from time step to a time step, right? So now we're going to think about the parameters as some form of autoregressive process. So the parameters today are a function of what they were yesterday plus some white noise. Okay. And in general, back up here, this model is written, because again, I'm being consistent with the literature on this. You often see that this matrix controlling potentially the autoregression will often have a time subscript as well, because that may vary with time. But in practice, and certainly all the models we use are going to have a time invariant G matrix here. An evolution matrix is what this is referred to. And in fact, in nearly all of the models, well, I think all of them will consider, we're going to treat GT as time invariant, and we're just going to assume it's an identity matrix. Okay, so if this is an identity matrix, you can imagine that going away, and that means that our parameters are going to evolve just according to a random walk. Parameter set today is a parameter set yesterday plus some white noise. So everyone's really familiar with random walk models now, so this shouldn't put anyone off. Okay, so in state space form, this is the way we would think about a dynamic linear model. So we've got an observation model that's going to relate the covariates to the data, right? So we have one observation at some time. We have an intercept plus some number of predictors, could be 1, 2, 3, etc. We have the parameters change with time, and we have an error. And then our state or process model determines how those parameters evolve over time. And in general, we'll think of this as a random walk, although it could just be some other, could be a mean reverting process, for instance. Okay, so to see the equivalence here between that DLM, the way the economists and other people write it, and the way we think about MARSS models, we just have to do some simple substitution. So in MARSS, we'll refer to this term as Z, right? So that goes down here. We're going to call the thetas X, and we'll refer to this error term as V. And then we already know that the thetas are the X's. Okay, so that one's there, this here. We're going to take G and replace that with B, and we'll leave W as it is. So this should be pretty familiar form now to everyone. you've got a single observation, multiple states, and here's the evolution of those states. Okay, so just by doing some simple substitution here, this is the way we would write this in MARSS form. And if you were going to try to solve this model using the MARSS package, for instance. Okay, this is a good time to revisit, now that we've talked about sort of state space forms for these models, how we're actually doing this. So in a DLM, we treat the covariates, the predictors, much differently than we would in a standard MARSS type model. So here, Z is the covariate and X are the parameters. But in a typical MARSS model, we've been saying, no, this is some mapping of states onto the observations, right? In a DFA model, these were unknown parameters that we tried to solve for. In a harbor seal example, these contain just ones or zeros. And then we said, well, if you've got covariates, those go over here. We've got the covariates at time t and the effect of those covariates, the parameters. So the setup for this model is very different. And this will tend to trip people up initially because we've been talking about these states as some kind of underlying truth, thing we can't observe. It's something we're interested in, some aspect of nature. And these are our observations. Now I'm telling you, the Z here are fixed and known covariates, and the X's are the parameters of interest. Okay, so regression models are just one type of DLM. There's any number of others. There's something that's called a stochastic level. We can think of that as a stochastic intercept. There's a stochastic growth, which we tend to refer to as something like trend or bias. And you can also include seasonal effects, right? These could be something like month of the year, or you might try to use some other predictor, like a discrete Fourier sequence based on sine and cosine waves. So let's think about the most simple DLM. And that is just what we call a stochastic level or a stochastic intercept. So here we say the observation at time t is just some intercept at time t plus error, and that intercept evolves according to a random walk. And
hey, Mark.
Yep.
I have a quick question. I know you were at the the Fish and Wildlife thing yesterday, and I forgot who was talking, but anyway, she talked about that she had random slope. Is that the same thing as what the stochastic growth model is doing? I'm trying to draw a connection on what she did with her data.
No, it's a little bit different than that.
Okay.
Well, but here, I'll back up for just a moment, Brielle. So even one more. So think about in this model here, actually let's back way up. Okay, so here's a term for an intercept. This is your design matrix, right? You remember that? Here's the intercept and here's the slope. In her models, this B has some subscript that denotes something like site.
Okay.
And then those B's are drawn from some distribution. So in this model, it turns out, well, you're going to see in a little while, we'll show you that you can make these a random effect as well. But the form of the random effects we're considering are always autoregressive processes. Like in 514, we talked about you could just draw it from a normal distribution with a mean of 0 or a mean of mu. In these models, the mean is always the value previous or with potentially some multiplier on it. So all random walks are random effects, but not all random effects are random walks. How's that for you?
Sounds good. Thank you.
As I like to say, a square is a rhombus, but a rhombus is not a square. So there you go. But that's a good question. And some of this will start to make a little more sense as we move along here, Brielle. Okay, so simple DLM, right? We just have an intercept and the intercept evolves over time. And that should look really familiar to everyone. If we just substituted X for alpha, we've got a random walk that's observed with error, right? Here's our random walk. And every time step, we don't get to see this perfectly because we've got some error on that we observe. So this is the model we spent quite a bit of time on in weeks 2 and 3 of the class. So all you can do is think about X here as a level, and it's changing over time. Okay, so here's a data set that's quite famous. It's contained in the base installation of R. Anyone can do this. Look for Nile River. And here's flow of the River Nile from the mid 1800s through kind of the latter part of last century. And if you stare at this for a while, you might say, you know, kind of looks like here's some level here, and then here's some level here. And your eyes are not mistaking you here. There was a dam that was constructed here. In fact, there were a series of dams that were constructed. So flows did in fact change. Well, we could fit that stochastic level model to those data, and it would look something like this. So instead of having some discrete jump, just two states, now the underlying kind of the intercept here is changing over time. And indeed, there was a fairly strong decrease here around the turn of last century prior to that. Okay, so that's a really simple DLM. In fact, the most simple DLM. So just backing up here for a moment, we'd call this model a random walk observed with error. Economists would refer to this as a stochastic level model. So if you ever hear that stochastic level model, you should know exactly what that is. You're like, oh, that's just a random walk with a fancy name on it. Okay, now let's think about a stochastic level model that's got some deterministic growth. So we're thinking about some fixed change over time. So now we're going to say, here's our level at time t, and that level is evolving according to a random walk, but we've got a bias term in here. Okay, so this is our growth in the other parlance. So same thing, if we just substitute alpha for x and u for eta, here's our biased random walk observed with error. So that's all a stochastic level with deterministic growth is. Okay, now let's get a little fancier. Let's consider a situation where both the underlying level can change over time and the bias can change over time. Okay, so we'll write the observation equation the same way. We're going to say that, okay, the observation today is just some level that changes plus error. And now we know that the underlying level is evolving according to a biased random walk. Here's our bias term. But now our bias is itself evolving according to a random walk. So both the intercept and the bias are going to change in this model. Okay, so how does one make this evolution equation match? So let me back up for a second. So this is the observation equation, and these two together are the state or evolution model here. So we have to figure out a way to actually get this to work mechanically. Well, to start with, what's informative to do is to write out this model with explicit coefficients on alpha and eta. So all I've done here is take this equation, or these two equations, and I'm rewriting them down here, and I'm putting ones in front of these three terms, and I'm adding in this term and putting a 0 in here just so these look symmetric, right? Both of these equations have alpha at t-1 and eta at t-1. But this one we're just going to multiply by 0 so it doesn't show up here. Okay, so that's all I did here. That's just this reprinted. Now, if we write this in matrix form, we pull the alpha and the eta out, and we'll stick that in a vector and call it theta. We're going to pull our coefficients out. 1 and 0 go here. 1 and 1 go here. We're going to call that G. And then we need alpha and eta to multiply by that. So this goes here, and this is just theta t-1, right? So we have the parameters today, the parameters yesterday, some errors, and then we have this evolution matrix here. And I told you early on that sometimes we just think of this as an identity matrix. So imagine that was 0 up there. That's what it would look like if it was just a random walk with error. I'm sorry, a biased random walk that didn't evolve. But now we need that thing to evolve, so we put it a little extra 1 in the upper right here. Okay, so if we think about this same model, but just writing it out in MARSS forms where we're not using all these Greek letters, we're just going to use things like X and Y. Here's our evolution. Here's the alpha, or the level rather. That's what it was yesterday, plus some bias term. And the bias term is going to evolve. So I just rewrote that again with explicit coefficients and pulled those down here. And we write this as x of t equals a matrix B times x of t minus 1 plus a vector of process errors. And the models up to today that you've seen like this just had a 0 in the upper right here for biased random walks. Okay, so that's how you can get both the intercept and the sort of the bias term to change over time. So this is why way back on the first day of class, we made a big deal about, you know, if you can get up on a whiteboard and write these sort of things out, or like this, we ought to be able to turn it into some matrix equation like this. And if we can do this, then we have some software that will help us solve these problems. MARSS will very happily work with this form of a model right here. Okay, that's the evolution of the parameters. So we've got an underlying intercept, that's going to change. We've got a bias in our random walk, that's going to change some. Now we need to deal with the observation aspect of this. So we said at the beginning, when we modeled this, we had the observation was just a function of an intercept only. There's no, we're not trying to add on some bias in here as well. The bias is contained within this equation, right? Let's go back up here. So here was the bias here. So alpha at t, so alpha t minus 1 plus the bias term. So we don't want the bias to show up here. So it's the same thing. I just rewrote this top equation by putting an explicit term for eta in here. And then once you do that, you can rewrite this equation in matrix form. So pull the 1 and the 0 out. That becomes x at t transpose. Pull alpha and eta out, that's our parameters at time t. So in MARSS form, it's the same way, right? We would just say y sub t is the x of t plus the error. Rewrite this where now we want a second x, but I'm going to put a 0 in here because I don't want it to really show up. And I'll just pull these two terms down, and in MARSS we'll call that z, and we'll pull the x's out and we call this x. Right, so this looks just like a MARSS model right here, the observation part of it. Oh, sorry, Logan, I missed your question. The underline is for emphasis, not to indicate that these are vectors of 1s and 0s. Yes, thank you very much. That is, it's truly just for emphasis. Yep. Okay, questions on that before we push ahead? So really the trick to all of this DLM thing so far is just being able to rewrite equations. Just take it right back to freshman algebra. Okay, so now let's think about a regression model here, where we actually have some predictors. And we want the intercept to change over time, and we want the slope to change over time. So Brielle, this is starting to get to your question. Well, the way to begin here is to rewrite that observation equation with, again, some explicit coefficients. So all I've done is pre-multiply alpha sub t by 1, and beta is being multiplied by x. Excuse me. Okay, and once we do that, then it's pretty easy to see how to write this in matrix notation. The 1 and the x just get pulled down. We call that x transpose. And we pull the alpha and the beta out, and we call that theta. And in MARSS form, we would have, this is a typo, that should be x2. So we'd have x1 plus x2 times z2. We have a 1 here, z here, pull those out, and we call this z. Then we pull our x1 and our x2 out, stick those here, and we call this vector x. So this is same model, just rewritten in our sort of standard MARSS form. And I'm kind of harping on this MARSS form of it because come Thursday, you're going to be using software to solve for the parameters in these models. So you're going to want to be able to write this sort of a model with respect to kind of MARSS notation. So Z's and X's instead of things like alphas and betas and thetas. Okay, the parameters in this case both follow a random walk. So here's our intercept. That's just a simple random walk. And here's our slope. And that's just a simple random walk. So this is pretty easy because we don't have to do any sort of algebra here. We can just pull these out. We'll call this vector theta. Here's theta at t minus 1. And here's our process errors, W. Right? And everyone's seen this before. Here's a MARSS form for two random walks. This is the intercept. This one is the slope. We have x at t minus 1, and W. Okay, let's expand our model now to think about seasonal effects. And this is probably perhaps the trickiest part here just to be able to keep up with as you're playing along at home. Okay, so now in this case, let's say we've got a linear regression model here. We've got some predictors, but we've also got some seasonality in the data. And in this case, the season is quarter. There's 4 quarters in a year. So here's our model, and it says alpha at t plus beta at t times our predictor plus some quarter effect. And we want that to be gamma 1 if it's quarter 1, gamma 2 if it's quarter 2, etc. This model looks great on paper, but it's pretty hard to implement in any sort of software and solve this. So we need a way to actually formalize this kind of if-then statement that I'm using here. Okay, well, let's just rewrite this equation with explicit coefficients like we've been doing. So I kind of skipped a step here, but you can imagine there's a 1 on this alpha. So we put that down here. We'll rewrite this so the x is the coefficient. So we'll put that down here. And then there's a 1 here. We put that down here. And then we have our vector of parameters, alpha, beta, and gamma. They end up in this vector. Okay, now we get to our evolution equation. So this is fine for an observation, but now we need to deal with this evolution of these parameters. Okay, so we've seen that we can set up the intercept as a random walk. We can set up the slope as a random walk. But now we have to figure out what the heck we're going to do with this quarter term, because we don't really want the quarter to be a function of last quarter. We want those to just be fixed things. So it goes, you have 4 terms in a year. They don't change among years. There's no t subscript here for time. Well, in this case, time might be a month, or I'm sorry, it might be a quarter. Okay. Well, we don't want the quarter term to evolve, so we could just put, well, let's just put quarter over here and we'll call this 0. So every time step, gamma is just gamma quarter. It's not changing over time. Right, we're starting to get closer. But now the question is, we still have to deal with that if-then statement I started with, right? If it's quarter 1, how do we tell this thing we'll pick off the quarter 1 term? And if it's quarter 2, pick off quarter 2. Well, we could potentially separate out the quarter effect. So here's our original model where we had an intercept, a slope, and a predictor, and a quarter effect. And instead, we're just going to say, all right, there's 4 of these. Let's just write them out explicitly in the model. So you have gamma 1, gamma 2, gamma 3, and gamma 4. Okay. And if we did that, we could rewrite it in matrix notation. So we have a 1 in front of this alpha, pull that down. We have an x, and I should have rewritten this. So x is, imagine it's in front of beta, pull that down. And then all these gamma terms just have 1s in front of them. So we pull that out, and then we'd have our parameter vector here. But we're still dealing with this situation where this model now, every time step has all 4 quarter effects, and that's not what we want. We only want 1 quarter effect at a time. Well, we could potentially set some of these equal to 0, right? So if it were quarter 1 and we made the coefficients on quarter 2, 3, and 4 all equal to 0, when we multiplied these two vectors together, we'd get this. Okay, oh, that's starting to look pretty good. Quarter 2, all right, we'll make this one 0 and now make this one 1, and these are zeros. So this is 0 times gamma 1 now, a 1 times gamma 2, and 0 times the other. So now we have gamma 2 in here. Okay, well, this is starting to look good. But the problem here now is, how do we know when we're going to be able to put 0 and 1 in here? Again, right, we're trying to think of this in sort of a large holistic framework. It's easy if we're just one off standing here trying to insert ones and zeros, but we'd like to be able to generalize this problem. Well, we could reorder the gammas. So let's leave this parameter vector. So here's for our intercept down here. Here's for our slope down here. And there's a 1 plus 1, 0. So at quarter 1, this will only pick off that term and it'll multiply zeros times these other 3. So you just have gamma 1 here. And at quarter 2, if we just reordered these, right, we just moved these 3 up and then stuck gamma 1 down at the bottom, we'd get what we want. Okay, so now we're at quarter 2, and you can imagine doing this again at quarter 3, and we'll just bump all these up and we'll put quarter gamma 2 down to the bottom, and that would work. But we still need a method that we can actually shift these things around without, again, just sitting there, you know, in a script in R, and every time step you're having to recode what this theta vector looks like. Well, the way you can do this is a little trick in linear algebra. So here's our evolution matrix G. And this is for our autoregressive equation on the parameters. So this term is for our alpha, the intercept. This term is for the beta. And now here we have this kind of bizarre matrix set up where we have zeros down the diagonal and ones up here above this, and then a 1 down in the lower left. And if you use this matrix lined up with something like this, and we had quarter 1 here, or we wanted quarter 1, so we'd have alpha, beta, gamma 1, gamma 2, gamma 3, gamma 4. We only want gamma 1 here. We don't want these other ones. So if theta at time t minus 1 was the intercept last term, the slope last term, oh, but instead it was quarter 4 last term and then 1, 2, 3, 4. This would say take 0 times that one, that's good. 1 times this one, that's good. 0 times that one, good. 0 times that one. Okay, so that term is right. And this is y2, so that says take 0 times that, 0 times that, 1 times y2. Okay, that works. And similarly, right? So this would be 0 times there, 0 times this, 0 times this, and then finally it would pick up gamma 3. And these aren't changing over time because these errors here are always set to 0. Okay, so if we then want quarter 2, would just be the same thing, because last time step, right, here's theta, let's call this t equals 1. So this was t equals 0. Okay, so now we're at t equals 2. And that's going to be, here's t equals 1, right, where we had a 1, 2, 3, 4. So if you did that multiplication again, it has the effect of doing this conveyor belt aspect. So multiplying a column vector times this kind of bizarre evolution matrix will just shift these things up each time step. And then when it gets to the top, it'll drop to the bottom, and then they'll shift up each time step and drop to the bottom. So it's sort of a conveyor belt aspect. And you could just iterate this along again, right? Here's quarter 3. This would work if this were monthly data, right? Instead of a 4x4 submatrix here, you'd have to have a 12x12. The diagonal would be all zeros, and above the diagonal, you would have ones, and then down in the lower left, you would still have a 1 sitting there. So if you have an R terminal open and you want, code up a matrix that looks like this, put 1, 2, 3, 4 there and multiply them together, and you should get 2, 3, 4, 1. Okay. questions on any of that before we talk about forecasting with DLMs? This is mostly a gee whiz thing. I mean, now that you know how to do it, you may want to do it in the future. But when I first learned about this, I was blown away. I was like, oh my gosh, that's going to work. And I sat there and I kept doing it. You know, as I opened up an R window, I kept, oh my God, it totally works. I could do it, you know, but, and you wouldn't, and I never would have come up with this just by sitting there, you know, thinking about it. Had I not read it in a paper somewhere else, I would just never come up with that. So anyway, that's how you can get the parameters to switch. You could use this construct outside of a DLM, right? In some other model where you're trying to only pick off a particular parameter at some given time step, this construct will work. So just something for you to keep in mind. And to Logan's question earlier, these lines in here are just convenience, just to help us identify that we're talking about the regression parameters and the seasonal aspects here. Okay. Oh, I'm going to back up one and foreshadow this. So we've been talking about these evolution errors here, or process errors, and we usually think of these as multivariate normal. And there's a variance covariance matrix, we call it Q. So you'd have to think about how you would set up Q to make this work. If we had a diagonal Q, you'd have Q1, Q2, and then 0, 0, 0 down the rest of the diagonal for Q. So Q would still have to be 6 by 6. It's not just 2 by 2. But most of Q would be zeros. It would just be in the upper left, you would have a couple little parameters sitting there. And all this other bit will be 0. And you'll see more of that in lab on Thursday. Okay, so let's talk about forecasting with a dynamic linear model. This is one of the ways that we see DLMs appear quite a bit in the literature, is in a forecasting context. And the idea here is that we want a prediction for time t based on the data up through this morning. So you imagine, like, you get up in the morning and the first thing you do is make a prediction before you get to look at your phone, your watch, anything. And the only information you have at that point is everything through yesterday. So you're going to want to make a prediction of today based on what you know in the past. Okay. So basically the pseudocode, sort of the recipe, the way this works is, okay, you're going to make a prediction for today. Well, we need predictions. So we're typically thinking about a model where we've got some covariates, predictor variables, and we have parameters that we want, but we don't know anything yet today. So we're going to estimate today's parameters based on yesterday's, because that's the best information we have. And once you do that, you make a prediction based on the parameters that you just chose based on yesterday's information. And now I hand you the predictor variable. You make your prediction. Then you get to see what the real value was today. Okay, now we observe what it was. Okay, well, we were off by a little bit, so then we'll update our parameters and then we'll do the same thing tomorrow. And then we'll go on, right? So that's basically the way this process works. Okay, so now we're going to get into the math. And I appreciate that this gets to be a little bit gory. So it's okay if you want to just sit back and let it wash over you now, you know, and you think about this later and tomorrow and the next day. Okay. We're dealing with autoregressive processes, and we typically just write those as something like x of t equals x of t minus 1 plus some white noise. But implicit in that is that if you kept going back far enough in time, at some point you're going to get to t equals 0, right? You had to start somewhere. Okay, so what are we going to say for our parameters at time 0? And in DLMs, we think about these parameters being in a vector theta, and that's at time 0, and this is given. So it's a conditional given the data through yesterday, right? So like I said, first thing in the morning, you get up, you don't know anything except what happened yesterday. Well, what we often do is we would typically say that the parameters are going to be equal to some vector, we're going to call that pi, plus some white noise today. And we treat these white noise as a multivariate normal with some mean, and I'm just going to call the variance covariance matrix lambda. And in the MARSS package, if you look a little bit further in there, you'll see that we refer to there's an initial state or x0. You'll see it in the output. And there's a distributional form to that. And it's essentially pi and gamma define that initial distribution. Okay. So what's the expectation for this parameter given this equation? Well, it's just pi, right? This is essentially, you can think of this as a mean. We're thinking about expectation, so ignore the W for now. Okay, so the expectation of the parameters at time 0 is just pi. The variance of the parameters is going to be the variance of pi plus the variance of the W's. Well, this is fixed, so the variance of that is 0. And the variance of W1 is right here. That's just gamma. So 0 plus gamma 0. So the variance of the parameters is lambda, and the mean is pi. Okay, so rewriting that, we would say the distribution of our parameters at time 0, given no information, we're back at time 0, is just going to be drawn from a multivariate normal with a mean pi and some covariance matrix lambda. Okay, so this is where we have to start. This is ground 0. All right, okay, so now it's today. That was yesterday. We took care of yesterday. Now we're like, okay, we're ready to go here. What do we need to do? Well, we think of our parameters as evolving over time according to some autoregressive process. So here's the parameters today, given the data from yesterday. Now we haven't seen any data today. And that's this evolution matrix G. That's going to be times the parameters yesterday, plus now some error. I'm just realizing that I made a typo. I have to go back and fix. This should say W0, W0. Okay. All right. Well, same thing. What's the expectation for theta 1? Well, that's going to be G times the expectation of theta 0. That's right here. And previously, we defined this expectation to be pi. So now our expectation today is just whatever the parameters in here were times pi. Recall that this oftentimes is just an identity matrix. So it would have no effect on it, which would just suggest that the parameters today were essentially the expectation was the same thing it was yesterday. Hasn't changed at all. Okay, so there's our expectation. Now we need to define the variance. This is what I was alluding to at the beginning of lecture. So here we've got G times theta 0 plus W1. So the variance of this term is going to be G times the variance of theta times G transpose, because they can't square a matrix. So this is the way we essentially deal with that, is G times G transpose. And then we're going to add the variance of W1. Well, again, previously we defined this to be gamma. So that's going to mean the variance now is G times gamma times G transpose plus the variance of this. Well, that's defined up here. So that's just Q. So now we know what the variance is today, and we know what the expectation is today. So now we have a distributional statement for our parameters today, given the data through yesterday, as a mean of G times pi, and it's got a covariance matrix given by this, G lambda G transpose plus Q. Okay, all right. The forecast function for Mars. Yes, thank you, Eli. That's coming up in another slide. I know as everyone's really starting to get a little freaked out about having to do this math, don't worry. Mars will do all this for you. You just have to pull out a couple of terms and you're done. Okay, so now we've got our parameters, right? Here they are. And so now somebody hands me the covariates. So now I'm ready to make a prediction. I want to make a forecast for what's happening at time 1, given the data through yesterday, our parameters today, and the covariates today. We don't know what Y1 is yet. We're going to make a prediction before we get to C. Okay, well, the expectation for this is just like before. It's going to be xt, we got this funny transpose, times theta, and the expectation of that here. And we know that the expectation of that was just G pi. So our expectation for y1 is going to be x of t times g times pi. Now we need a variance statement here. So we need to know what the variance of this is plus the variance of that. Well, same thing before. This is going to be x transpose times the variance of theta 1 times x plus the variance of E1, and that's defined up here. So that's just R. That's a scalar now. So if we write all that out, we could substitute in this term, which from the previous slide, right, was this bit. So we take x transpose times that quantity times x plus r. So if you do all of this matrix multiplication, you'll get a scalar. And it's just adding to this. So the idea here, right, is that the errors have some uncertainty in them, R. The uncertainty in our forecast begins with that, but then we have to add in this additional uncertainty owing to the parameters and the predictors. That's all these statements are saying. Okay, so if you want to then write out the distributional form, so here's the distribution of our forecast for today, given the data from yesterday and all of our parameters. And that's going to be normally distributed because this is a univariate, it's just a scalar. So this is a normal, not a multivariate normal, with a mean of x transpose times g pi, and then this variance term right here. Okay, so if you want to put all of that together, it looks like this. You have a distributional statement for the initial states, where the states are the parameters. Then you know, okay, moving forward at any given time, the parameters at that time step, given the data through yesterday, are multivariate normal. And you have to deal with this evolution matrix on here, so that inflates the variance as well as the mean. And then the distribution of the forecast itself, given the data through yesterday, is now just normal. And here again, it's going to be whatever your theta was times the covariates plus your observation variance inflated by the variance in the states, where here those are parameters. Okay, and as Eli said, good news, people. This is probably the last time you'll ever have to dig into this in any detail, because MARSS is going to make that really easy. MARSS is going to return all these terms for you. You just have to know where to find them in there, but it's doing all this in the background. So you're going to be very happy. Okay. So diagnostics for dynamic linear models. Oh, there you go. See, Eli just wrote something in the chat now. There's a forecast function for MARSS, which will do that for you. Okay, just with any other models that we've been talking about, we should have a pretty good understanding that our fitted model meets the underlying assumptions, right? So in like a linear regression context, we often think of things like IID errors, independent, identically distributed, those sort of things. Well, it's pretty easy to calculate forecast errors because you just know what your forecast was and you know what the data was, and the difference in those two is your forecast error. And we pretty much have assumed in these models that we're talking about today that all of these are normal. We've often used a different variance term here, but in general, they're all normally distributed and they should be independent. So that if we did check the covariance or the correlation between residual today and the one yesterday, it should be 0. So you can check this assumption using a QQ plot. And in R, that's really simple. It's just QQ line. We'll do it. And you could use an ACF to check this, right? You could just hand it your vector of residuals and say, ask for the ACF of that. And it will compute that very simply. And you've seen the examples of that already. Okay, questions on forecasting. And I should denote that the diagnostics here are necessarily only looking at forecast errors, you could be looking at just the regular observation errors here, same thing. Okay, so as Eli's pointing out in the chat again, Eli has made a lot of this really easy for you. Don't ask her how many hours it took her to deal with all of this. It's like probably days and days of her life gone, never to be recovered again. Okay, so dynamic linear models. Basically, the thing to keep in mind is that it's a model. Dynamic just means that the parameters are changing. And you can see that that could be something like an intercept. It could be a bias term in a random walk. It could be the regression parameters. Any of those, we have the ability to make them change over time. Logan is giving you props, Eli. Yes, I know. We will. Someday I will show you the download statistics for the MARSS package. It's pretty impressive. Not everyone who's downloaded it uses it, but you make some assumption about what percentage of people who download it end up using it. There's a lot of people running around in the world using this package. Okay. Let's now expand this notion of a dynamic linear model to a multivariate response. So those models that we talked about so far have been a situation where the response, the y at time t, was just a single value. It was just the temperature in Seattle today. But now let's imagine we wanted to model the temperature in Bellingham, Mount Vernon, Seattle, Tacoma, and Olympia, all of them today. So we had a multivariate response, right? We've got temperature at multiple locations. Well, that's not too hard to do, actually. It's just, again, you have to do a little bit of matrix math, but once you understand the gist of it, it's pretty straightforward. Okay, so let's think about, we talked about the most simple univariate DLM was just a random walk observed with error. Well, now the most simple multivariate DLM is going to be multiple observations of a stochastic level. So now we have a vector of observations, right? Here's our temperature in Bellingham, Mount Vernon, Seattle, Tacoma, Olympia. And this has we need a matrix here, Z, to map the data, the observations onto the states. And we want a stochastic level. And so we're going to set the stochastic level up to be just a univariate random walk. And since this is univariate and this is multivariate, Z here has to be a column vector of ones. And this is no different than those models that you saw earlier. We used a model just like this when we were thinking about harbor seals. Right? This basically says there's just one large panmictic group and that all of your observations are just seeing one state here. Okay. So this is, in MARSS terms, just multiple observations of a random walk, right? So I wrote this out originally where this was this kind of stochastic level. Just think of this as X and this being your standard random walk. No different. Okay, so the most simple multivariate DLM is just multiple observations of a random walk. Another really simple DLM in multivariate space would be multiple observations of multiple levels. So here now we've got the state is the same dimension as the observations. They're both n by 1 at time t. And the way we do that is by making Z the identity matrix. Right, so this is, again, just like we did with harbor seals. This was a case where Strait of Juan de Fuca, North Puget Sound, and South Puget Sound were all their unique states. So each observation was just observing its own unique state. And in MARSS terms, we think about like this, right? We use X to denote states. Here's a multivariate random walk. Here's multiple observations of that random walk, where Z is the identity matrix. And I bookended two extremes here, but we could do something different where we had Z, the columns of Z were less than the rows. So maybe this was 1, 1, and 1, 1. So we had 2 random walks and 4 observations of them. Right, so it would be no different than those models we've seen so far. Okay, now we're going to move into slightly more complicated but more interesting models. So now let's think about that regression model again, right? Where we had a univariate response before, and we had some predictors in here with an intercept, and then we had the parameters that would include something like a slope and an intercept, maybe even quarterly effects. But now we want this response to be multivariate. So it's a vector here where it's n by 1 and n is 2 or more. The thetas here is still a vector. The errors now are a vector instead of a scalar, and the coefficient, or sorry, the predictor variables have this funny aspect to them here. We're going to expand this matrix, where before this was just a row vector, just had one row, and we wrote it with a 1 and like an x1, something like that. And this funny symbol that looks like an X with a circle around it's called the Kronecker product, for those of you who are unfamiliar with it. Okay, well, what is a Kronecker product? Kronecker product is a way of multiplying the entries in two different matrices without doing your standard matrix mapping. So if A is, let's say it's an m by n, and B was p by q, the Kronecker product of A times B is going to have dimensions m times p, so it'll be that first dimension times that first dimension by n by q. And the way you would write this out would be A11 gets multiplied by B, A m1 by B, A n1 by B, and then this is still a matrix here, right? So now we're essentially, imagine replicating this matrix as many terms as you had in A, and this thing gets to be really big. And here's an example for you. So let's say A looks like this. It's 1, 2, 3, and 4. And B is double that. It's 2, 4, 6, and 8. So the Kronecker product of A by B is you pull out 1 times B, you pull out 2 times B, 3 times B, and 4 times B. And you may remember from first week of class, right, that a scalar times a matrix, you can just multiply those through. So this was 2 by 2, and this is 2 by 2, so the product of them needs to be 4 by 4, and that's what we see here. So 1 times this matrix, well, that's just itself. 2 times that, there's double. 3 times that, 3 times, and 4 times that, 4 times here. Oops. Oh, I didn't mean to do that. Okay, so a regression model where now let's say we have 2 observations, so n is 2. And here's what we said that observation model looked like. Here's a vector. We take the predictors with a Kronecker product times the identity matrix. And they have parameters plus error. So let's write that out. So here's our 2 observations. X of t, let's say we only have 1 predictor. So we have put a 1 in for the intercept. Here's our 1 predictor. N is 2, so here's a 2 by 2 identity matrix. And now we have a parameter vector or 4, where we have 2 alphas, because we need alpha for y1 and an alpha for y2. And we have 2 slopes, because we need a slope for this one and a slope for that one. So here I just rewrote that same equation from the last slide. And now I'm just doing this Kronecker multiplication. And that multiplication here will result in this form. So this was 1 by 2, this was 2 by 2. So the dimensions final have to be 2 by 4. Okay, so that just looks like an identity matrix here. And now we have the same covariate on a diagonal here. And this should make sense just by looking at this matrix math. So here it says y1 at times t is 1 times alpha 1. Okay, there's our intercept. 0 times alpha 2, because yeah, that's for the second model. We don't want that in. X of t times beta 1, that's good. And then 0 times beta 2. Okay, that's good because we didn't want that in there. And analogously, that's what y2 would be. You don't want the intercept from model 1, but you do want it from model 2. You don't want the slope from model 2, or 1 rather, but you do want it from model 2. Okay, now we've got a multivariate DLM. So the observations are multivariate. So now we've got an issue where we're not just dealing with a simple scalar like it was with univariate models. Right now we're dealing with a situation where the observations are multivariate, the observation errors are multivariate. So we need a covariance matrix to figure that out. And the question is, what are we going to use here? You know, are we going to use diagonal and equal? These are IED, diagonal and unequal, equal variance, covariance, some bizarre thing that we code up ourselves where they all have different variances and some of them are covariating with one another, others not. Well, oops, sorry, I didn't mean to do that. This is basically user choice combined with parsimony, meaning start simple. This is my best advice at this point is I would start with something that looks a lot like this and then think about maybe this or this before you start getting into something like this, because in theory, these are all parameters you're going to have to estimate. Okay, so that was the observation part of a multivariate DLM. Now we need to deal with this evolution of the parameters. And in our univariate case, univariate response, the parameters were still a vector, right? We had an alpha and a beta in here, an alpha and a beta in here. In one, we even had some gammas for quarterly effects, and we had this kind of funny G matrix to pick out the correct quarter. Okay, so if we had two regression parameters and we had two responses, just like that other one, that means we have two intercepts and we have two slopes. And G here would be 1 by 1 because we need something for the alphas and something for the betas, and that's I2. But now we need to expand this. So here we said it was G Kronecker product I. We're going to replace G with I. So now we're just going to do the Kronecker product of two identity matrices. And the good news is that this math is super simple because any two identity matrices that are multiplied by a Kronecker product just result in a large identity matrix where it's just the combination of these two dimensions. 2 by 2, 2 by 2, the result has to be 4 by 4, and it will itself be an identity matrix. So as long as you've chosen a DLM where G is identity, this is really easy. It's not actually that hard if you didn't choose one without, because in R, there's, that's how you do a Kronecker product in R. So it's instead of using an asterisk like you would for matrix multiplication, you just substitute that with an X and it will do Kronecker products. So if you want to convince yourself that's the case, try this example. Code one up where you call A this and B this and do the Kronecker product of that. You should get this matrix down here on the right. Okay. So to simplify that, right, if G is identity, all of this goes away and you're just left with your really basic random walk here. So the intercepts are going to be a function of the intercepts last time plus some errors. The slopes will be functions of the slope last time plus some errors. Okay, same thing here. You've got now, right, as we did before, and I kind of glossed over this, you've got an evolution of your parameters here. This is a multivariate random walk. So the errors are multivariate normal, covariance matrix Q, and the question is, what do you want to choose for Q here? Well, you could expand this a little bit and think about it this way. So you might have multiple alphas here, right? If there were two, this would be, there'd be two of them here, and betas, there'd be two of these. And I've just sort of stacked these in notation. And you could imagine, well, we'll have mean 0 for all of them. And we might want a covariance matrix for the intercepts that's different than the covariance matrix for the betas. So each one of these in and of itself would be a square matrix. So in our example where we had two alphas and two betas, you'd have a 2 by 2 matrix here, 2 by 2 matrix of zeros, 2 by 2 matrix of zeros, 2 by 2 matrix of this. So in this notation, the idea here is that just substitute any subscript in here you want, and then choose some choice. And in this case, I've just said, well, it's diagonal and equal. There's no, these parameters are all the same, and there's no covariance terms in the off diagonals. Okay, you could do the same thing where it's diagonal and unequal, right? Now I've subscripted these so that each one of these is unique. The other thing to imagine is that you could think of a model where alpha, the intercepts are evolving over time, but you want fixed slopes. You don't want the slopes to evolve. So if you wanted BT to be equal to BT equal to BT equal to B at all time steps, all you'd have to do is set this lower diagonal part of this to be a 0 as well, right? Because it would say the expectation here, let's back up one so you could see this in a, I thought I had that broken out in one of these. No, my bad. But same notion like when we were looking at quarterly effects. If we didn't want those to change, then we want the covariance matrix to be 0 there. So same thing, you could say, I want a time invariant intercept. That's going to stay the same way it is, but now I'm going to let the slope move a little. This would just be set to 0 up here, and this little bit down here would then be Q. Okay. You want to get really crazy, you could make this thing unconstrained. So, you know, the alpha has a bunch of different variances, and there's covariances among all of them. The betas, same thing, it's got a thing. But in practice, you're going to want to keep Q and R, for that matter, as simple as possible. And that has nothing to do with this particular application of MARSS or DLMs. It's just in general when we're doing this. I always encourage you to start simple and try to keep it that way as long as that works. Some people will set these models up so that these two would be exactly the same as well. There's ways in the literature that actually they'll relate one of these to another, and they'll actually make it a function of the observation variance. That's a little bit trickier to do. We can't actually set those up in MARSS to work that way, but you have a lot of flexibility here is the bottom line. And when doing this, I strongly recommend you keep this very simple. Think about diagonal matrices with no covariance, and think about keeping the variance terms relatively simple. The other part of this is you should think about the system as a whole, just like we've been doing in general, right? Where if you know something about the system you're interested in, you know, is there reason that if you had multiple intercepts that one should vary like crazy and one should barely move? And same with the slopes. Do you want a slope that swings all over the place, or do you want one that just barely changes? And do you think that should be different by location or species or whatever you're trying to do? Okay, so in summary, we talked a lot about univariate response DLMs, where you just have one observation at time t. And you saw you could set up stochastic level and growth models. Those are essentially random walks observed with error, or biased random walks observed with error. And then we got really fancy and made the bias term actually change a little bit. Then you saw dynamic regression, where the parameters for the model were changing. You had a slope and an intercept, both of those were changing. You saw how to use that kind of funny form for G to deal with fixed seasonal effects. Everyone's going to go to bed dreaming about forecasting with the DLM. You're going to see those equations going on. That'll put you to sleep for sure. Forget counting sheep. Just try to reconstruct the variance covariance matrix for a DLM in forecast mode. Then, like I said, it's important to consider model diagnostics. And we haven't emphasized this a lot in this class, but we will moving forward. There'll be some points where we'll talk about that. But just like any other statistical modeling exercise, when you're done, you should see if your model is meeting your assumptions, right? And in the univariate case, that's super easy. You can calculate the forecast errors. You can ask, hey, are they normally distributed? And are they independent? And then we saw how to expand this multivariate response or expand the DLM, I'm sorry, into a multivariate response where you had more than one observation. Okay, in lab on Thursday, you will get a chance to fit these kind of models using MARSS. And that will be your opportunity to be completely amazed by how much this software is doing for you behind the scenes. But when pressed, you will be able to tell someone exactly what's going on behind the scenes in MARSS, perhaps with a couple of crib sheets next to you, but right, you now know how all that is working. Okay, questions or comments about any of that material?
I'll just make a comment that I think that these dynamic linear models are one of the most powerful methods that you are going to learn in this class for addressing problems that you're going to come up, that we come up with really often within fisheries and environmental science. And, we want to understand, like, not just what's the effect of this covariate, but is the effect of this covariate changing over time? Or is, something like, is the seasonality changing over time? Which we know that that's definitely happening, say, with, as the climate's warming. And these types of models can get at that question.
Okay, everyone can see these slides all right? Okay, so this is something I've been playing around with for a while, and I really need to actually sit down and write up because this just came up in an online forum with some other people where people are starting to think about this. So I'm interested in ecological portfolios as a general concept. And one of the things I've been thinking about is how you can use models from economics, where they build portfolios all the time, to apply those to ecological systems. So here's basically a really quick example of that. Okay, so Eli was involved with this a little bit, and a former student at SAFS, actually, Jen Griffiths, who at the time was a postdoc at Stockholm University. So for those of you who are unaware, ecological portfolios are a really hot thing in the world right now. And these are just some titles from some papers that were published in the last few years, for that matter. So if you think about risk in a finance world, there's two different forms. And the first one is what's called systematic or market risk. And this affects entire markets. So something like the 9/11 terrorist attack impact global economies, right? It didn't matter which market you were invested in, which commodities, everything took a nosedive after 9/11. The second kind is what's called unsystematic or asset risk. And that's really specific to a specific security or industry. So the idea here might be droughts are going to affect commodities like corn, but it's not going to have any influence on oil production. So the idea is that if you have a portfolio, you should be able to reduce that unsystematic risk by doing something like this, right? So here's two portfolios. This one has 5 colors, 1 unit of each. This portfolio has only 2 different colors, 2 of these blues and 2 of these. Okay, so now imagine we had some large market force. And this is slightly dated, but it went over better a couple of years ago. So somebody with a lot of influence in the world says so-called aqua is fake blues. Sad. Okay, so now aqua is really tanking. But in this portfolio, that's 60% of your holdings. This one, it's only 20%. So this one is relatively well buffered from this one. Okay, so now think about systematic risk here. So this is a situation, same exact portfolios, and some large market force comes in and says, black and white is winning, colors are all losing. So it doesn't matter what you have here, all of these are colored in your portfolio, so all of these are going to tank. Right, so that's sort of the idea between risk commodity. Okay, so the idea is that when you're building a portfolio, you need to know something about systematic risk, things that you can do something about. And way back in the 1960s, there were several economists who were sitting around thinking about this, and they came up with something called the market model. And the market model is really pretty straightforward. It just basically says the returns of an asset are a function of the manager's skill. So imagine we're buying like mutual funds here. And it's also a function of what's called the correlated volatility and the returns of the market itself. So you've probably heard volatility comes up in the news all the time with respect to markets. And then there's going to be some residual error, things that people have no control over. So we could write this model out like a really simple DLM, right? So here's the returns of our asset at time t, here's the manager's skill, here's the volatility, here's the market returns, and here's the error. And this beta term here is what's basically giving us a level of our systematic risk. Okay, so if you want to think about what that beta means, if it's 0, that means the asset's completely independent of the market. So it's really not influenced by large field forces. And in economics, an example would be fixed yield bonds. So you buy 30-year treasury bonds. Those rarely move. I mean, it takes an enormous amount of political and fiscal policy to drive any change in a bond market. If that absolute value of beta is between 0 and 1, then it's moving less than the market as a whole. And you could think of these as staple stocks. Things like Johnson & Johnson, you know, the things that we all buy on a daily basis. If it's 1, then it's exactly tracking the market, and that'd be something like an index stock. So like the S&P 500 has 500 stocks in it. If you bought a portfolio that had those exact same 500, your beta is going to be 1. And if the beta is greater than 1, that means it's sort of volatile and it moves a lot more than market changes. And those are things like tech stocks. Okay, so along these guys are thinking about this back in the 60s, and they're saying, you know, if we know something about an asset's risk, the expected return of the market, and the expected return of a risk-free asset like treasury bonds, then we could basically figure out a way to value these securities. And they did this via the security market line, as they call it. So here's the way this model works. You plot a model's risk down here on the X, and here's the return of the asset here, and here's a line. And the intercept of this line is the value of the return of that risk-free asset. So this is your 30-year treasury bonds. The slope is the difference between the market and this free thing. And the risk here is your predictor. So the price of the asset is the intercept, treasury bonds, times the difference between those times your risk. So, okay, so we're considering a bunch of stocks for portfolio. Anything that lies above that line is undervalued, and those are things that we want in our portfolio. Anything under that line is overvalued, and we would rather not have those in the portfolio. I would like to point out that these 3 gentlemen won the Nobel Prize in 1990 for a linear regression model. So lest everyone think linear regression has no place in the real world, you can get a Nobel Prize for doing this, all right? Okay, so let's make this a little more interesting. I'm interested in, like I said, ecological portfolios. I've done a lot of work on salmon. I'm going to take you through 1,000 miles east of here to Central Basin, Idaho, and the Snake River and Salmon River Basin. And here we have a whole bunch of populations that form what's called an ESU, an evolutionarily significant unit. And those are colored here. So you could think of these populations now as assets in a portfolio. And I need to figure out a way to calculate returns. And I'm just doing the change in log density over a generation. And a generation for these fish is roughly 4 years. So all you do is say, what's the difference between points that are 4 units apart? That's the return of an asset. Okay, so that one went down, that one went up. Okay, so here now are the returns in sort of log survival of all of those populations in my potential portfolio. And you can see that it varies, right? There's some years pretty good, some years where it's really bad in general. Some of these tend to bounce around a lot, like look at Loon here. Oh my gosh. Okay, now I need some sort of market return, some sort of large scale force. And in the salmon world, we know that once they go out to the ocean, that's a real synchronizing place. So in freshwaters, lots of diversities, habitats are very different. Things are doing all kinds of unique things. You get out to the ocean, that really tends to synchronize things. So PDO, for instance, there's cool and warm phases. Depending on the way that is, you can synchronize salmon returns across huge portions of North America. So sorry, I'm just going to jump ahead here a little bit to get to the interesting stuff. So here's our time series of PDO. And the PDO was sort of typified by periods where it's generally warm, then generally cold, generally warm, generally cold, warm, cold. Okay, so now I need to figure out what's my risk-free asset, my treasury bond, so to speak. And in a conservation context, if a population can replace itself, that's pretty good. So the log of replacement here is just 0, so I'm going to assume that the risk-free asset return is 0. Okay, so now we need to estimate beta. And you could assume it's static, or you could pass a moving window, or you could use a DLM. Okay, and I'm going to cycle through here because everyone just saw all this. Okay, so here now are my time series. This is years going across the X, and here's the beta at time t for all of these different populations. And I've shaded this area between -1 and 1 because remember, that's an area where they're considered non-volatile, and anything greater than 1 or less than -1 is considered to be volatile. So what you'd really like to see is something that just hovers right around the 0 line. Like this is not a bad asset at all. This one has had some real changes over time, right? It used to move in synchrony with the large scale forces, then it was kind of independent, and now it's sort of moving out of synchrony. Grand Ron, this thing is kind of weird. Here's some that have gone through some really high peaks. Okay, so now if you plot the returns versus risk, you can do something like this. So here's our security market line. These are undervalued, so these are the ones we want. These are overvalued, the things we don't want. And all I'm going to do now is subtract that difference. So we're taking the residuals from this line. So here's those points that are above it. Here's the points that are below it. And now I'm going to show you what that, whoops, here's that risk, the beta. And I'm doing this in a forecast context because in this situation, we'd like to have some idea what's going on in advance. And here's the return in that following year. And so I'm going to plot these by decades. That's what the colors are. Okay, I'm just going to step you through the time series. Oh, and see what's going on. So now if we were thinking about this in a portfolio context, we'd be looking for those which are moving around here and hopefully would be in positive territory here. So good ones, as it turns out, are things like Sulphur. Let's see, Big Creek is a pretty good one. Bear Valley's pretty good. Then you've got situations like the Grand Ron over here and the Yankee Fork, which tend to be really volatile and move all over the place. So from an ecological portfolio perspective, we may not want to invest as much in these or this one as say something like Secesh or Big or something like that. Oops. Okay, so there was my deep dive into ecological portfolios using DLMs in 7-8 minutes. So that's the idea. So like I said, this type of analysis that I just did here with an ecological portfolio, there's people that are making way more money than all of us combined on Wall Street right now who are doing this every day. They get up and this is what they do. So yeah, so these things are, you can see now that there's some real, and on the class website, I shared, there's a reference to a paper that I did years ago with a former colleague at NOAA, where we were looking at forecasting climate change climate-driven changes in fish survival using a DLM as well. That was a univariate case. There was only one group that we were looking at, but anyway,